as we prepare to head in towards calculus, after all, this is a calculus class again, we need to take some time to think about what are our flat things. You see, we like to take our subjects that we're studying, oftentimes functions, and say, hey, locally they look flat. Let's use the flat thing to understand their behavior. So, what are our flat things? Well, we still talk about things like lines, but now that we're moving up, we can have a new flat thing, planes. So, it's going to be a plain and simple idea today as we talk about our flat stuff. Well, let's begin. So let's start with what we're most familiar with, which are lines. We know lines. Now, oftentimes when we think of lines in 2D, we say, hey, two important pieces of information. You need a point and a slope. Well, we're still going to have the same idea. We're going to need two important pieces of information. Point and direction. You see, one of the things you can think about what is slope doing is it's telling us how we're changing, which tells us how we move. And so really, slope is a direction stored as a number. Now we're going to take our direction and store it as a vector. So what do we have? Well, we have our point, so x0, y0, z0, and our direction, a, b, c. Now, what do we do? Well, what we do is we say, look, suppose I have any other point on the line. So there's a different point, x, y, z. Then what's true is if we look at the vector there, so the vector from our initial point to some arbitrary point, it's pointing in the same way as ABC. Or more appropriately, it's parallel to ABC. Well, that means it's a multiple. So we have that the difference between the points is a multiple of our direction vector. Now we move things around because we have two vectors which are equal to each other, and lo and behold, we can say, look, here we go. We can say that our line has the following description. Any point, x, y, z, which we're going to temporarily think of as being a vector, so x, y, z is sort of a vector that represents the point x, y, z, is a combination of our initial point where we start plus moving some amount, so we think of t as how much we move, in the direction of the line. So in other words, every single point on the line is found by picking an arbitrary point to start and moving along it some amount. And of course, we can move in both directions. All right. Now this is called the vector form because everything says a vector. Well, what we can do is we can say, look, vectors have components, and let's break it down. So how do we break it down? Well, we say, okay, let's look at the first entry. You have x is the x naught plus t times a. So x is x naught plus at. Similar, y is y naught plus bt. Z is z naught plus ct. And that's parametric form. Now, the nice thing about parametric form is it's really easy to put a line into parametric form and also to read information out. Because if you look, what do you see? Well, you see that there's this column here, which is our point, and then right next to that is another column, and if you look at the coefficients of t, a, b, c, that's our vector. And so, if we're given our point in our vector, we can just instantly write down our parametric form. And if we have our parametric form, we can, well, whatever the sound of snapping going backwards is, we can write down our point in our vector. There is a word of warning, and it's not a bad thing. It's sort of like just something to be aware of when comparing answers. Vectors are not unique if we talk about direction because you can scale, and the points are not unique on a line because you can move around. So what happens is you can talk about, well, here is a way to write the line. But it's not the way to write the line because you can vary the point and you can vary the vector. So keep in mind that it's possible for two people to actually have the same line, but when they compare their answers, they look completely different. That's all right. That's okay. Now, there is one other way that you see lines represented. And in some sense, you might say, well, look, there's this extra aspect, this t. What if I didn't want the t? In other words, somehow remove it from the equation. Is it possible? Well, the answer is yes, it is possible. How do you do it? Well, what you do is you go through and you solve for t. So for instance here, you could say you subtract by x naught, divide by a. So you could say, look, t, it's x minus x naught, divide by a. But same process. You would get y subtract y naught, divide by b. Well, it's still t, so you get y minus y naught, divide by b. And if you subtract and divide, you get z minus z naught, divide by c. So this format here, we're not going to use it too much, not because it's not correct, just because it doesn't really have as much automatic intuition. The things I like about the vector form and parametric form is you look at it and you're like, boom, I see what I need. I see a point and I see a direction, and away I go. Whereas when you write it in this way, you're like, what? What's going on? It's not so clear. It's not so clear. And this is known as symmetric form. So if you ever hear a symmetric form, that's what they're referring to. All right, so there's our lines. Okay, pretty straightforward, easy to do. Just make sure, if you're ever asked to find a line, always ask yourself, okay, I need to have a point and a direction. And between the two of them, the direction will be the interesting part. Direction is almost always the interesting part whenever you're looking for things. Now, let's do a little fact. Suppose we're given some point here, P, and we have a line, and it goes through a point Q, and we have the direction vector, V. And the question is, what's the distance from P to the line? Well, the way we always talk about distance, whenever we say what's the distance between things, we always mean the minimal distance. The nice thing is, in geometry, we know when we talk about minimal distance, we're always going to have right angles involved when our objects are flat. Because sort of the notion is, if it weren't a right angle, I can improve. And you might, well, why? Well, you see, you can imagine if I went down here, so I said, look, suppose I look at this, and I said, that's not a right angle, and I compare it to the right angle, well, you get a right triangle right away. And what's true about a right triangle is the hypotenuse is always longer than the other sides. So that this distance is going to be greater than that distance. So the nice thing, as we were saying, is we know there's a right angle involved. So that's helpful. That's good. That means there's some foreshadowing that there might be Pythagorean theorem or possibly some type of trigonometry involved. Now in this case, when we look at this and say, okay, what can we do? And, well, we know what we're shooting for, but let's suppose we didn't know that. And we said, well, can we just figure it out? Well, we say, let's see what we have. Right now, we don't have much. We have a vector and some points. Well, let's make a new vector. So let's talk about this vector. So we can draw a vector that goes from the point Q to the point P. And now we say, well, look, we have a triangle. And of course, it's not just any triangle. It's, as we said, the right kind of triangle. But there's something else we have. You'll notice in one corner of this triangle, we have two vectors involved. We have our vector V and this new vector we just found. So we can say, look, let's put an angle there. So theta is the angle between our vectors QP and V. All right, so now what do? Well, we think about which side do we know, which side do we want. Now, I claim we only really know one side. And you might say, well, wait a second, how about the line here? Don't we know that side? we know the direction of that side, but we don't know the length of that side because we don't know how v is in comparison to the length. It might be exactly the length, might be shorter as in this picture, might be much longer. Could even be pointing the opposite direction. We don't know. But we do know exactly the length of this other side. The length of this other side is the magnitude of the vector that we threw in. So we say, okay, we know something about the hypotenuse. We have our angle. We want to know something about this other side. So we say, well, this is the side we want to know about. So according to trigonometry, the opposite and the hypotenuse are related by sine. So sine of the angle is the opposite divided by the hypotenuse. Okay, now we're most of the way done. Why? Because now we can say, good, the thing that we're looking for is equal to the length of this vector that we found times the sine of the angle. But now we start thinking about, okay, we've learned things about, vectors, about dot products and cross products. And there was one place where sine showed up. Sine showed up in the cross product expression. And in particular, we'll do a little side note, recall that if we take the magnitude of u cross v, that was the magnitude of u, the magnitude of v, sine theta. So we say, well, perfect. See, we got a sine theta already. We have one of the vectors involved. So if we just put in the magnitude of this other vector, then we've got a cross product. So we say, great, put it in. So we'll make this the magnitude of v times the magnitude of qp times the sine theta. And I go, aha, now. But let me say, whoa, hold on. We can't just throw stuff in arbitrarily. We've got to maintain balance. Okay, so how do we do it? Well, we've got to do something which would cancel out the addition of this new piece. And the way we do it is divide by the magnitude of v. And now we're like, perfect. So what we have upstairs, very clean. It translates into the magnitude of this cross product, qp cross v. And downstairs, the magnitude of v. And we're done. Good. Now, one thing you can do is you can check, is it reasonable? Well, how can we check at least something that says, okay, this at least makes sense and it's a reasonable thing to do? Well, suppose you looked at the following case. Suppose P, actually we're already on the line. Now, what's the distance from P to the line? Well, the distance has to be 0 because it's already there. Now, if we look at the vector QP in this case, what do we see? Well, QP and V are parallel. And if you take the cross product of two parallel vectors, what do you get? You get 0. It goes away. And the magnitude of 0 is 0. And so that says, okay, this is a reasonable answer, because at least in that case, we're getting the right answer. Of course, it's true. I mean, we worked it out. We have it all there. So there you go. Now you have a way to say, look, you give me a point, you give me a line, I can tell you how far that point is from that line. All right, well, now let's go to our new flat object, which will be planes. Now, in some sense, this will be our preferred flat object, because as we get into multivariable functions, we're going to say, look, the thing that's really being approximated is something that looks like a flat plane. Think of a plane as, if you will, like a sheet of paper. Now, what do we want? When we had lines, we had a point and a direction. So what we'd like is to have, for planes, a point and a direction. Now, it seems like, okay, well, that should be easy, but things get complicated. Because think about a plane. You can even think about the xy plane if that helps. Which direction can you go in the xy plane? Well, the answer is you can go in lots of directions. So if I'm at a particular point, what can happen is I can move in many different ways. There's a lot of freedom involved. but not complete freedom. I have to stay in the plane. So the problem is there's not one single direction that a plane contains. In fact, there's many, many directions that a plane contains. So how do we get down to one direction? Well, now we use the fact that we're in dimension 3, because we're going to stick in dimension 3. And if we think of a plane as being two-dimensional, that says, well, look, if I have 3 dimensions, and I've used up 2 dimensions on my plane, I have 1 dimension left over. And that would be the direction that's perpendicular. So when we talk about the direction, we're actually going to talk about the following. It's the direction which is perpendicular to the plane. Now, when we say it's perpendicular to the plane, a nice way to start thinking about it, think about the xy plane and the z-axis. Well, what happens is no matter which direction you go, it's perpendicular to each and every one of these directions. So when we talk about the normal vector, we say that the normal vector is going to be the vector which is perpendicular to all vectors in the plane. So that's what we mean. So if you hear the word normal, it's a good way to think about it is perpendicular. So we want to be perpendicular to the plane. So in some sense, when we're focusing on the plane, it's the normal vector where we want to put our energy. We're going to spend the most amount of time figuring out what is our normal vector. And when we want to answer questions about the plane, it's the normal vector which is usually going to give us the answers that we need. So keep that in mind. As an example, suppose I have 2 planes that cross each other. So I have 2 planes that cross each other, and I ask, what's the angle? Well, now, of course, that's not so obvious, right? So if I draw 2 planes, and, well, that's a challenge in and of itself. So let's suppose we can draw 2 planes, and here's the line of intersection. Okay, so there's these 2 planes, they cross, they form an X of some sort. Of course, they could form sort of a shallow X, almost perpendicular, any angle you want. Now the question becomes, okay, how do we look at the angle between planes? Well, it's not so clear right away. But what we can do is we can say, let's change our perspective. Now, that's actually a really important idea, and one which we're going to use very frequently in the future. Now, when we say change our perspective, we say, well, let's look at things in a different way. So let's look straight down the intersection. So we're going to take our situation and turn so that were we to look, that line that corresponds to the intersection of the 2 planes would all coalesce right on top of each other and would become a single point. So what happens then? Well, once we've changed our perspective, our planes are now going to look like lines, because from our vantage point, it's all sort of collapsing on top of each other. And now we say, okay, so when we talk about the angle of intersection between the planes, now it's a little bit more reasonable to talk about. We say, well, look, our angle is one of these angles here. Well, they're really just supplementary angles. So these are the angles that we're going to be after when we talk about the angle of intersection. But it still becomes the question, well, how do you find angle between planes? Well, we think, how do we find angles? Well, we know how to find angles between vectors, so let's transform our problem and say, all right, instead of finding an angle between the 2 planes, what we'll do is we'll say, if we look at the normal vectors, so the normal vector to one of them will be here, the normal vector to the other one will be here. And if you look, what happens is the normal vectors are essentially, because they're perpendicular, it's like we're doing a 90-degree turn. So therefore, the angle between the planes is the same as the angle between the normal vectors. So that's what we mean here. So if we're looking for the angle between planes, transform that problem, angle between normal vectors, and we say, hey, we have tools for that. We can do something. We can make progress on that problem. So that's one example of why we like to use normal vectors. It's a really convenient way to talk about what's going on. Now, okay, that's the idea of planes. How do we get to the formula? Well, it's actually fairly straightforward. So what do you say? Well, let's suppose we have our plane, and we know our plane has a point. So we're going to think of our point as being this point right here, x0, y0, z0. We have another point on our plane. X, y, z is just some arbitrary other point on our plane. We have to figure out how to describe the plane, but right now we're just saying x, y, z, some other point. And then we have the normal vector, a, b, c. So remember, when it comes to describing the plane, there's really two pieces of information. We have the normal vector and the point. So these are our two pieces of information. Now what we need to do is think about, all right, how do I go from my two pieces of information to a formula? Well, we think about what things represent. The normal vector is perpendicular. It's perpendicular to any vector in the plane. That's what normal vectors do. They're perpendicular to what's in the plane. So we say, hey, we have our given point in the plane, x0, y0, z0, and we have an arbitrary point in the plane, x, y, z, so we can put a vector between them. So that would be the vector x minus x0, y minus y0, z minus z0. And now we say these two vectors are perpendicular, or, better word, they're orthogonal. There's a nice property about orthogonal vectors. Vectors are orthogonal if and only if their dot product is 0. So now we have the idea. 0 is the dot product of the two orthogonal vectors. So we do the dot product. A times x minus x naught. B times y minus y naught. C times z minus z naught. Now you do a little bit of expansion. You'll get a times x, b times y, and c times z. And then you get some other stuff. Now here's the key. This other stuff, a, x0, b, y0, c, z0, only depends on the information given. It only depends on our initial point in the plane and the normal vector. It doesn't depend on anything about x, y, and z. So we're going to collapse all that into a single term. We'll call that d. So now what do we have? Our plane is ax plus by plus cz, that part. We move the d across, equals d. So that's it. That's what all planes look like. And any equation of this form is a plane. So it's really easy to talk about planes. So in particular, and this is a really important point, if you have the equation for a plane, you can grab the normal vector. Because what do you have? The normal vector is a, b, c, and there you go. And of course, if you have the normal vector, you can get the ax plus by plus cz. You just plug in the right pieces. So now it's really quick to switch back and forth from equation to a plane to normal vector to equation to the plane. But what about the d? Okay, so first off, what is this d doing? In some sense, you can think of the following. If I have an equation for the plane, ax plus by plus cz equals d, and I change d, what's happening is I'm just sort of doing a shift of the plane, moving it up and down along in the direction of the normal vector. So that d acts as a shift. That's what d can be thought of as doing. How do we find d? Well, once you know the normal vector, then all you need to do is you say, look, I know it's ax plus by plus cz equals something. Plug in any point on the plane, any point at all, it doesn't matter. And say, okay, what is a times the x coordinate? What's b times the y coordinate? What's c times the z coordinate? Whatever it turns out to be, that's what d needs to be in order for the equation to work. So now we say, look, planes are beautiful. We just have to say, let's find our normal vector, let's figure out a point, and life is good. Life is beautiful. And why shouldn't it be? We deserve life to be nice every once in a while. Okay, good. So let's do one more idea, which is talk about distance. We did distance from a point to a line. Let's do distance from a point to a plane. That seems like it should be a fun problem, right? All right, so here we go. We're given a point P. So here's our point P, x1, y1, z1. And we have a plane, ax plus by plus cz equals d. And our goal is, what's the distance from our point down to the plane? And we actually have the answer, other than, whoops, I missed an absolute value sign. There we go. Now we have the answer, ax1 plus by1 plus cz1 minus d. Whatever that is, take the absolute value of that, divide by the square root of a squared plus b squared plus c squared. And you're probably thinking, well, of course it is. Ha-ha. Well, maybe that's not so obvious. We're going to figure this out. We're going to figure out why this is true and go through the argument here. One thing, of course, you can say is it reasonable? Well, suppose you started with a point on the plane. If x1, y1, z1, if this point were not here, but say we're on the plane, what would happen? Well, when you plug it in to ax1 plus by1 plus cz1, you'd get d, because that's what it says. Every point on the plane, this expression would be d. D minus d is 0. So you'd say, aha, the distance from a point in the plane to the plane is 0. So that's actually good. That agrees with our intuition. So in some sense, what you can almost think of happening here, we talked about as you change the value for d, you're moving it back and forth in the normal direction. So what's happening is you have this ax1 plus by1 plus cz1. It's sort of saying, okay, this is how much we think we should shift up along. The d is how much we actually shifted along. Now, why the other term? Well, we can think of the other term saying, well, we have to just make sure that our vector, normal vector, has somehow been normalized so that the length of the vector is not important. So in that sense, it almost makes sense. Even without a proof, we're like, okay, this sounds reasonable. But we're going to have a proof. And then, of course, we don't just have to say, well, it sounds reasonable. It will be reasonable. An even better situation. So we think about, all right, let's suppose what can we do? Well, let's pick some point in the plane. Now, of course, we'd like to say, haha, that's our point we should pick, right? The nearest point. That's the one we should go after. Well, maybe it's not so easy to find the nearest point. Maybe it is. We'll get into that. But let's suppose we have some arbitrary point. So here's the x0, y0, z0. I don't know what it is. It's just some point in the plane. Now, I will tell you, it's actually pretty easy to find a point in the plane. Because what you have, if you think of your equation, you have 3 variables, but 1 equation, which means you have a lot of choices you can make. So you say, okay, let me make x equals 0. Let's let y be 0. And what makes z work out to be true? And then you have a point, 0, 0, something, d over c in this case. So it's very easy to find a point. And it's not so easy, maybe, to find the point. But okay, so we found a point. And we do what we always do when we talk about vectors. We say, well, look, there's a couple of vectors involved. We can talk about this vector. We can make it. And why? Well, what is it? Well, it's the vector between the points. So we have this vector, x1 minus x0, y1 minus y0, z1 minus z0. So that's the vector between the 2 points. And then we say, well, is there any other vector? Well, of course there is. There is another wonderful, wonderful vector. Anytime we're talking about a plane, we always will think, hey, there's an important vector involved, and that is the normal vector. It's a vector that we'll normally think about, because normally it shows up a lot in these types of problems. Okay, so now we start thinking, what do we want? Well, what would be good? If we think about our triangle here, and there is a natural triangle involved, add this side. So we add this side, and we complete that side. We see, look, it's not just any triangle, it's the right kind of triangle. We say, all right, good. Well, what do we want? Well, we know something about the hypotenuse. We can nail that down. We know it precisely, so that's good. What else? Well, if we think about what angle can we find, the answer is we can actually find this angle up here. Now, where does that angle come from? One of the things you can see it coming from is if you take our original vectors and you just sort of push them along. So, for example, you take this vector and push it so it comes out. And you take n, similar way, you push it so it starts there and goes up. Then you say the angle between those two vectors, n, and the vector we found between our 2 points, is going to be the same. These angles are the same. Okay, so now we have the angle in this corner. And what do we want? Well, we want to know the length of the adjacent side. That's what we're after. We don't care about the length of the opposite side. That just says how far apart the point x0, y0, z0 is to this point that we're kind of interested in. But that's not what we want. We want to know how far the point is down to there, down to the plane. So we say, aha, here we go. What we need to do, we need to take the hypotenuse. Now the hypotenuse is the magnitude of this vector, x1 minus x0, y1 minus y0, and z1 minus z0, times the cosine of the angle between the two vectors, n and that vector. All right, so let's start with this. Here's our distance. I've already told a small lie. So I'm going to fix my lie. Why is this not true? And how is it easy to fix? Can you see what the fix is? And why it's not true? Well, the fix is a little bit easier to spot. Cosine could be a negative value. Okay. So take the absolute value. Now at this point, you're probably thinking, whoa. When we talked about the sine before, we didn't worry about whether it's positive or negative. Why do we have to worry about the cosine? Well, if you think about the angle between vectors, so if I have my two vectors here, what are the angles? Well, they're going to go from 0 to 180. That's it. See, if I go past 180 over here, then what happens is you just say this is now the angle. So the angle is always less than or equal to 180. Now, if you think about the sine function, it's always positive in that range. But for cosine, it's positive and negative. So if you think about cosine of 0 is 1, cosine of pi halves is 0, cosine of 180, or pi, is negative 1. So you have to worry about the sine. Now I say, okay, I see how I have to worry about the sine. Where does that show up in the picture? Well, I kind of made an assumption about n. Remember, the vectors are not unique. And normal vectors, we should say this, are also not unique. What can be true? Well, normal vectors you can scale. So if we go back to our generic equation for a plane, which we had here, we said, look, this is sort of the equation for the plane. Well, almost. What you can do, though, is you can scale both sides. So if I double A, B, and C, and D, it's still the same plane. It's a little bit better than lines. Lines are just all over the place, hopeless. But for planes, it's a little bit more controlled. Usually we choose A, B, C, and D so that the numbers are nice relative to each other. Usually we like things like whole numbers. It's nice to be whole. So what's my little misdirection here? Well, maybe n was actually pointing down. And in that case, if I come here, well, the angle would actually be this angle, which is an obtuse angle. And that's why we need to worry about the absolute value. The good news is, if I look at the absolute value of the cosine, they're equal for both these two values. So no worries. We're fine. So now we start saying, okay, where did cosine show up? Well, it did show up. And the place it showed up is it showed up inside of the dot product. So let's do a little side note. So recall. So that u dot v was magnitude of u, magnitude of v, cosine theta. So we have a magnitude of the vector, the cosine of the angle. We just need the magnitude of the other vector. So we say, okay, easy to fix. So this will become And I'm going to put the absolute value attached to the whole expression. So the absolute value of the magnitude of x1 minus x naught, y1 minus y naught, z1 minus z naught, times the magnitude of the normal vector. Well, what is the normal vector? We haven't written it down, but it's easy to read off. A, B, C. A, B, C. So magnitude of A, B, C, cosine theta, and then the other absolute value. Okay, but of course we can't throw in a magnitude on the top unless we also do it on the bottom. And now you can see, aha, that is the square root of a squared plus b squared plus c squared. We're on track, and we are. So now our big thing is to figure out, okay, how do we simplify the numerator? So to do that, we say we know it's a dot product. So we have this is equal to the absolute value of the dot product of a, b, c with x1 minus x naught, y1 minus y naught, z1 minus z naught. So we'll just make a little note here. This whole thing here is a, b, c dot x1 minus x naught, y1 minus y naught, and z1 minus z naught. So let's do the dot product. You'll get a, x1 minus x naught, plus b, y1 minus y naught, plus c times z1 minus z naught, all over downstairs to square root a squared plus b squared plus c squared. Okay, so we're almost done. Look at the top. Let's write it out. So we'll put ax1, then by1, okay, and then cz1, great. So that takes care of the first pieces off of every one of the three terms. Now we're going to subtract the second pieces. A times x naught, b times y naught, c times z naught. And divide by the square root of a squared plus b squared plus c squared. Okay, now, last thing to look at. We're really close. We've got the absolute value. We got ax1 plus by1 plus cz1. We got that square root downstairs. What happens to this? Well, we claim it's d. Why? Well, notice x0, y0, z0 is not something arbitrary. It's a point in the plane. And every single point in the plane satisfies the relationship. ax0 plus by0 plus cz0 is d. And that's why this last piece, because we're in the plane, this is going to be equal to d. And therefore, we're done. That's the formula. Wow, beautiful, beautiful. And so it's a kind of a nice way. A lot of geometry involved. In fact, that's going to be the case here. You'll see in the last two problems where we had, well, distance to a plane or distance to a line, we use dot products and cross products. So really there's going to be three sort of important tools. We're going to emphasize this many, many times. The dot product is useful when you know two things are orthogonal. We're going to use the cross product extensively. The cross product is great for making things which are orthogonal. And the last thing is geometry and geometric intuition. And that one requires practice and some thinking and analogies. Think about, okay, what's the situation? Let's draw a picture. Let's draw a rough picture. Make sure we don't sort of mislead ourselves. So that comes with more practice. So let's go and do some practice. All right. See you soon.